In this section, we'll cover complex numbers. As a reminder from Algebra 1 and Algebra 2, I is equal to the square root of negative 1. So, therefore, we can find three other values for I squared, I cubed, and I to the fourth. I squared is equal to I times I, and therefore is equal to the square root of negative 1 times the square root of negative 1, which is basically just negative 1. I cubed is equal to I squared times I, and therefore if I squared is equal to negative 1, we end up getting negative I. For I to the fourth is equal to I squared times I squared, which means it's equal to negative 1 times negative 1, which is positive 1. Therefore, the pattern is I, negative 1, negative I, 1. And I say a pattern because look at the next problem, the first example problem. I to the 29th power. This pattern here would just keep repeating itself. It's like an SAT problem, a remainder problem for only SATs. If the remainder is, this here is 1, 2, 3, and 0 remainder. So, if I see I to the 29th, I take 29 divided by 4 because there's 4 numbers in this pattern, and we end up getting 7 with a remainder of 1. Therefore, this would go through 7 complete cycles and then be stuck back at the first one. So therefore, we would get I. If we look at the second example, I to the 6th minus I to the 11th, 6 is 6 divided by 4, which is 2, remainder of 2. Therefore, we go through 2 full cycles and then have 1, 2. So the first one here is equal to negative 1. The next one, I to the 11th, would be 11 divided by 4, which is 1, would be 2, with a remainder of 3. Therefore, you come here, 1, 2, 3, this would be equal to negative I. So it's minus negative I, which therefore changes to negative 1 plus I. Let's practice some more operations of complex numbers. Number 3. Let's simplify the square root of negative 36 plus the square root of negative 9. Well, the square root of negative 36 is 6i, and the square root of negative 9 is 3i. Therefore, when we add those two together, we get 9i. On number 4, we can add complex numbers and subtract them just like we would add or subtract common variables. So if I distribute this, we have minus 3 minus 2i, and therefore we can add the i's together and add the numbers together, which gives us negative 9i plus 2. On the fifth problem, we can multiply, just like we multiply variables of this nature. This problem here is a binomial times a binomial, therefore we can FOIL it. So 2 times negative 6 is negative 12, 2 times negative 5 is negative 10i, 7i times negative 6 is negative 42i, and 7 times negative 5 is negative 35i squared. We can now simplify this. Again, we should always reduce the exponents of I using that pattern above. So I squared is equal to negative 1, so this becomes a plus 35 minus 52i minus 12. So the final answer is equal to 35 minus 12, which is 23 minus 52i. For the division of complex numbers, you have to remember what I is. I is a square root, and just like last year in PST, when you covered the algebra review, radicals cannot remain in the denominator. So in the end, we must get this out of the denominator by multiplying by its conjugate, 2 minus 3i. When we multiply it, the bottom is the easy one because we have a difference of squares. We get 2 times 2, which is 4, and we get 3i times negative 3i, which is negative 9i squared. Again, we still have an I in that denominator, but if you remember, I squared is negative 1, so this is really 4 plus 9, which gives us 13. So all we have to do is work on the top now. 3 times 2 is 6. 3 times negative 3 is negative 9i. Negative 4 times 2 is negative 8i. And negative 4i times negative 3i is plus 12i squared. So when we rewrite this, we have 6 minus 17i. And again, I squared is negative 1, so we have minus 12. Which reduces to negative 6 minus 17i over 13. On this final answer here, if we could reduce these numbers, we would. But since there's no common number that goes into 6, 17, and 13, it is not reducible. I have two final problems. I have another division because this is what you guys generally do not like. Again, we must get this I out of the denominator, so we multiply by its conjugate. The bottom should be easy. It should reduce nicely. 3 times 3 is 9, minus I squared times 5. So that's going to reduce to, if we change this to a negative 1, this changes to a plus 5. So we get 9 plus 5, which is 14. On the top, 2 times 3 is 6, plus 2i the root of 5, plus 3i the root of 5, plus I squared times 5. So plus 5i squared. So when we add these together, we end up getting 6 plus 5i the root of 5 minus 5. When we reduce this, we end up with 1 plus 5i the root of 5 over 14. The last problem is kind of a difficult one because you don't know exactly where to go. We could start by converting each of these higher exponents to a different form of I. So I squared to negative 1, I cubed to negative I. That would work. But I noticed that we can factor out an I, and that which would cancel with this denominator. Therefore, if I factor out an I, I'm left with I plus 2i squared all over I. These i's then cancel, and we're left with I plus 2i squared. Therefore, this can be converted to a negative 1, so it becomes I minus 2. Complex numbers, though they may seem impractical, will be a huge part of our lives next year, especially in chapters 11 and 12, where they become an integral part of a different perspective of mathematics. This should set you up for covering section 5 on the summer assignment.